Greetings and welcome to the Chemistry 222 Molar Mass Determination of a Volatile Liquid Lab. Oh, that's got a long name. Let's just call it the Volatile Liquid Lab or something like that. But anyway, we're actually going to do some measurements in this lab. So we'll use some of the quantities we've used before, such as milliliters, degrees Celsius, etc., and also some new values like millibar and atmosphere. All of this revolves around finding the molar mass of a liquid that can be easily vaporized. And vaporized here means it's turned into a gas. If you can turn it into a gas, then you can use the ideal gas law. And from the ideal gas law, it's not too hard usually to find the molar mass of your substance. This process we're going to look at in this video is wonderful for finding molar mass if your liquid can easily turn into a gas, all right? If it doesn't turn into a gas, then it would be harder to find the molar mass with these kind of techniques. We'll look at other techniques for finding molar mass coming up soon. So without further ado, let's get into this lab. So as I stated earlier, in this lab, we're going to try and find the molar mass of a substance which is a liquid naturally, but it's volatile. And volatile means it has a pretty good vapor phase over it, and that means that it turns into a gas pretty readily, all right? So if you have a liquid that turns into a gas relatively easily, which usually means under the boiling point of water, by the way, but anyway, then this process works really well, and it's really slick how this thing works out. Finding the molar mass is always important to chemists, all right? We need that for, say, stoichiometry, for turning grams to moles. If you have some kind of solution stoichiometry, sometimes it'll be helpful to find out how much mass is in your solution. Lots of different reasons why finding molar mass is important. So this is a cool kind of technique to have. The ideal gas law is PV equals nRT. And I'm hoping you've seen this already somewhere, but if you haven't, let's just go through it real fast. P stands for pressure, the pressure of the gas. V is the volume of the gas. T is the temperature of the gas. And N, which is a symbol we'll use quite a bit in the future, N stands for moles. Most of the time in chemistry, if you see N, it stands for moles. We'll use that a lot here coming up. The only one I haven't talked about yet is R. R is called the gas constant, and there's several versions of this gas constant, and we'll talk about other ones later, but the one we need for this lab, R equals 0.082057. And that's a number that, believe it or not, we're going to use quite a bit. So make sure you memorize / write it down / put it in your calculator. We're going to use that quite a bit. Now, the units of R are going to dictate what we need to use for pressure, volume, and temperature. So look at the value there of R, and right next to it, it says liters, atmospheres per mole per Kelvin. Mole minus 1 means, to the minus 1 power, means like 1 over moles. So in this context, it would be like liters, atmospheres on top, and then in the bottom, you'd have both moles and Kelvin. So the units of R, liters, atmospheres per mole Kelvin. Because of the units of R, we have to have a pressure that's in atmospheres, ATM. We have to have a volume that's in liters, and we have to have a temperature which is in Kelvin. So all of those things will be important. Probably, and most of the time in the lab, we won't use liters, atmospheres, and Kelvin. We'll probably use like milliliters or centimeters cubed for volume. We'll use, who knows, millimeters of mercury or millibars for pressure, usually Celsius for temperature. But when we use the ideal gas law, we must use liters, atmospheres, moles, and Kelvin. So how this works is we'll solve first for N, the moles, and then if we know how many grams of unknown we put in, grams divided by moles N will give us the molar mass. And that's how this process works. And it's really cool as long as your liquid is relatively easy to turn into a gas. Here's a little bit more on the units. So again, pressure has to be in atmospheres when you're going to plug it in PV equals nRT. And there's different kind of conversions you can use, and depending on your lab, you may or may not need some of these. 1 atmosphere, which again is the ATM symbol, is equal to 760 millimeters of mercury, and that's also equal to 1013 millibar. So depending on if this is an actual lab or a virtual lab, you might need 1 or or the other. All right, no problem. It's also worth mentioning that a torr, T-O-R-R, 1 torr equals 1 millimeter of mercury. So if you see 760 torr, that would also be 1 atmosphere. Now, volume is in liters, and there's 1,000 milliliters per liter. And also what's helpful to remember, we haven't done this for a while, is that 1 milliliter is equal to 1 centimeter cubed. Milliliters and liters are usually used for liquids, and centimeters cubed are usually used for solids, but they really are interchangeable. So if you see one or the other, you can convert them easy. Kelvin temperatures are really important in this lab. Kelvin temperatures are never negative, and for us, never zero. So if you have a Celsius temperature, which could be negative, you want to add 273.15 to it to get the Kelvin temperature. Likewise, if you have to go from Kelvin back to Celsius, you take your Kelvin temperature and subtract 273.15 from it. And then again, moles is just moles of gas. If you really want to make this a quick and dirty one-stop equation, all right, you can do it. So normally what people would do is they'd have N equals PV over RT, and then the molar mass, MM, would equal the mass in grams divided by the moles. But if you substitute in for moles PV over RT, you do end up with this kind of quick and dirty equation right here. And it doesn't matter which path you use, you can still solve for N equals PV over RT, and then molar mass G over moles, or you can just do it all in one thing. Any way you want to do it, totally cool. I am the lazy chemist, and I will try and introduce as many of these kind of time-saving techniques as possible, but feel free to use or discard them as you see fit. It's no big deal. So in this lab, what you're going to do is place a sample of liquid in what's called a round bottom flask. A round bottom flask is real common in organic chemistry and a lot of synthetic chemistry classes where you're making things. Round bottom flasks are great because they distribute the heat a lot more regularly than if you had like a beaker or something. But anyway, you're going to put that round bottom flask in water, and then you're going to heat the water around it using a Bunsen burner. And the way this round bottom flask is set up, the excess unknown is going to literally boil out. It looks like a percolation. If you've ever seen an old school coffee maker, the coffee percolates, and that means that it's getting ready to be done. A percolation, or to percolate, just means the extra is kicked out. You'll actually see like drops coming out of this little top part and stuff. After a while, though, the percolation stops, and that means that the gas has reached equilibrium with the amount of volume in the flask, and that's pretty cool. Once you get to that part, then the boiling water temperature should equal the temperature of the gas inside, because at that point, everything's set up and stuff. So if we measure the outside water temperature, that should equal the temperature of the gas inside. The volume of the round bottom flask at that point should equal the volume that the gas is occupying as well. So you can see here what we're doing. We're just getting just the right amount of unknown for the volume of our flask. And at that temperature, then you can see how these pieces are all going to fall in together. And then finally, because there is a little hole that this excess stuff is percolating out of, there's always atmospheric pressure pushing down on us. And if the percolation, if the extra stuff coming out the little hole stops, that means the atmospheric pressure is also equal to the pressure of the gas. The gas is holding its own, it's pushing back against the atmospheric pressure, but they're equal. We can use a barometer to measure the pressure at this point. That's going to be the pressure part of the ideal gas law molar mass calculation. So again, we're going to wait until this percolation thing is done. The boiling water temperature will equal the temperature of the gas. The volume of the flask will be the volume of the gas, and the atmospheric pressure should at that point equal the pressure of the gas pushing against it. As the round bottom is pulled out of the boiling water and allowed to cool, you'll see that inside the flask that some of the unknown recondenses as a liquid. If the liquid is volatile, that means it's also probably easy to get back into the liquid phase once it's turned into a gas. So if you take a measurement of how much of the unknown is left, i.e. empty round bottom, and compare it to the round bottom after heating, the difference between those will reflect the mass of your unknown. So that little g in the mm equals GRT over PV, that's how we're going to find that. So it's pretty cool how this lab works out. All of those little pieces can be figured out. And again, R is just a constant. That's that 0.082057 number. In this lab, we're going to perform the experiment twice, all right? And you're going to do two separate molar mass calculations, all right? You'll have two values for the molar mass. You can use those two values then to find the average molar mass, and then we'll do a parts per thousand analysis of the molar mass values. And if you haven't done a parts per thousand in a while, I totally understand. Parts per thousand is a measure of the precision, how close the measurements are to each other. It basically indicates like how close the experimenter was when they did the experiments, all right? You want a smaller number for parts per thousand. Smaller numbers mean better precision. Bigger numbers mean not as good precision. We're back in the world of significant figures in this lab. In the last labs where we drew Lewis structures, we didn't think about that too much, but oh, we're definitely back there now. So try and watch that. Also watch out for the units, all right? Most of the units we record in the lab will have to convert over before we find the molar mass. So that's obviously something. This is a lab where if you do it in the lab, we will have to have safety glasses on all the time, because the safety glasses will keep us, our eyes hopefully safe from everything. So just be aware of that. And then finally, the last thing you want to do in this lab is find the volume of the flask. Once you're done with all the measurements, you can literally fill the flask up with water completely to the brim, as much of the space possible. And you can take the mass of the flask with the water. And if you subtract the empty mass of the flask, then that's going to be the grams of water in the round bottom. If you know the density, you can turn the grams into a volume of water in the flask. And if you've done a good job making sure the volume of the water is the volume of the flask, voila, you've got the flask, and that's going to equal the volume of your unknown compound, your unknown gas. So it's pretty cool. That'll be the last thing you do. It does make the round bottom kind of wet and stuff. You have to dry it off. So that's why we wait until the very end. Okay, if you do have any questions, of course you can ask me. There's no dumb question, that's for sure. So please let me know. Okay, at this point, let's watch a video to see how the molar mass of a volatile liquid lab actually goes. This is a fun lab, like I said, and you definitely want to make sure you wear safety goggles during the whole part, because we're going to have boiling water and gases, and it's going to smell. You don't want to eat or drink in the lab. It's nasty. You want to watch your electronics next to the chemicals, because they'll be splittering out and stuff like that. Just be careful in this lab, but it is kind of fun, and it's a powerful tool for chemists. Anytime you can find molar mass, it's pretty cool. Okay, let's see how the lab will work. Let me know if you have any questions, and have a great day. Good luck on your lab.